Good afternoon, everybody. Let's start the lesson today. Our course is Electromagnetic Engineering courses, and today, chapter 3, I would like to present about magnetic field. Okay. So for the chapter 2, we know about the electrostatic. Obviously, the question raised, what is magnetic field is? What is magnetic field? So the question, what is magnetic field? Can some student answer the question? What is magnetic field? Okay. Normally, when you have a field, for example, you have gravitation field. Okay. So of course, there is the gravitational forces. We have the electric field, so we have the electric forces. That's the Coulomb law, okay, about the Coulomb forces. So every time when you have the field exists, there is the forces. Okay. So we have the magnetic field, we have the electric field, and then we combine electric and magnetic field together. We have the electromagnetic field. And that's why our course is about the electromagnetic engineering. And we have the chapter 3 is about the electrostatic, chapter 4 about the magnetostatic, and chapter 5 about the electrodynamic. So today, the questions for today is answers, what is a magnetic field? Some students can answer my question. Okay, you will also learn from the high school. Okay. Okay, so we present this. Now, so look at this slide. So our course is about the Maxwell equation. Okay. And here we stay here. Magnetostatic. And the last chapter, electrostatic, we already finished. And now we stay here. And then futures. The future we continue studying about electromagnetic wave. Okay. And related to electromagnetic wave, we have the transmission line theory, Kirchhoff law, circuit theory. Okay. And finally, we come up with the application. We will have the application of electromagnetic engineering. I would like to present about some application, probably application for antenna. And now here you stay here. Okay. We are staying here. Okay. Okay, so to answer the question, we come up with the lesson. So topic number 1, electric current. Electric current. Some students can tell me what is the electric current? What is the electric current?
In my opinion, electric current is a stream of charge within a steady direction. In a direction of steady.
Thank you. I think is Correct, but not completely. Okay, not completely. It's a flow of charge. Okay, but we carry a charge, and the direction is agreed. Okay. So magnetostatic is branch of electromagnetic dealing with the effect of electric charge in motion. Okay. And the magnetic field is produced by CD current. Okay, it's about the magnetostatic. And here about the electric current. As you know already from high school, it's not new. Electric current is simply the flow of charge. Here electron flow in a wire constitute current. So you should specify about the charge here is electron. To measure the electric current, we use the unit coulomb per second or ampere. So a coulomb or an ampere refers to amount charge crossing through a crossing section area per unit of time. Its equivalent that you have 1 ampere is 6 times 10 power 18 electrons per second. Electron flow in the direction opposite to the current. It's for indication. Okay, I will explain this point. For example, okay, in this circuit you have the sources, okay, UI, for example, and it connected to resistor R, okay, and when you indication that this is I, right, it's a direction of I, right, that the indication about the circuit, electric circuit, okay, but actually the direction of the electron is opposite to the direction indication of I. So that's the point. Okay. Okay, we go through. About the definition. If you have the differential charge dq move perpendicular to the surface of area S in a time dt, then informing by definition that I equal dq by dt. So the definition of current, that is the amount of charge over unit of time. Yeah. So you have 1 ampere equal 1 coulomb per second. Okay. And we go to the point by convention. The direction of current is the direction of flow of positive charge. Actual charge carry electron. Here they move to the opposite direction to I. So it's nothing but it's emphasize the point of the last line. Okay. So pay attention that it's a definition of I. Okay. We continue to the point number 1. We continue talking about the electric current. And now we come up with the theorem. What we call it Stokes theorem. Stokes theorem. Okay. So what the Stokes theorem statement? Stokes theorem statement. Okay. So here we define the current density design. Current density design. Okay. Which have the direction of flow charge and magnitude is quantity of charge which flow perpendicular to the unit surface area in unit of time. Okay. So that's the definition. So by definition, you have the I, the current I, which is the derivative of charge per unit of time. But Stokes theorem states different, that you can constitute the current by integration of the psi density over the area S. Okay. Yes. So you take the integration of the density, current density, go through the total surface S, you obtain the current. Okay. This is the Stokes theorem. Okay, we continue. Now we're talking about the fundamental law of electric current. Fundamental law of electric current. So, someone can tell me what does this mean when we're talking about the fundamental law? Fundamental law. Fundamental law. Or in Vietnamese, fundamental. What does this mean? Fundamental. Fundamental law. It's good. Cơ sở. Cơ sở. Nền tảng. It's correct. In our university, for the third year, for the 2 year, for the third year student, you always learn about the fundamental law. Until you go to the fourth year and you take the thesis, okay, thesis work, then you come up with a new thing. And most of the time you work with fundamental law. Okay. In Vietnamese, nền tảng, các định luật nền tảng. Okay. So, what the fundamental law we study today is the conservative law of charge. Okay. Conservative law of charge. Conservative law of charge. Okay. Okay, so look at left side, the left side. You have the Q here, which is the integration of rho dV. Okay? So for the charge density rho over the object with the volume V, you have the charge Q equal integration of rho dV. You already know about this. Okay. And from the Stokes theorem, you have the I, which is integration of psi S over the surface S. Yeah. Okay. Now, by definition, with the electric current, which is the derivative of Q over the time t. Okay. Okay. So here Q, you take the derivative of Q over unit of time. So you take the derivative of rho dV over unit of time. So here the right side is come up from Stokes theorem, and the left side is by the right side is come from definition, and the left side is come from Stokes theorem. Okay. So we continue to write this. You have that you put inside that minus integration of derivative of rho to t dv. Okay. Okay. However, you have the Gauss formula, which is relation of the surface and the volume formula. Okay? So that you have from Gauss formula that integration over S, G ds equal integration over V dot G dV. So that from Gauss formula is the dip G dV. Dip G dV. Okay. It's nothing but it's jump from the surface to the volume. Okay. So when you And when you agree both sides, okay, agree both sides, so you have current I is Gs over Gs and derivative of rho dt over V, okay, that is equal dg dV, okay, and then you make the conclusion that dg equal d rho by dt minus d rho by dt. So that's we make the conclusion, and that's the conservative law of charge. Okay. Okay, I will not ask you to remember all the logical sequence here to understand, but you should keep in mind the physical meaning of the fundamental law. That if G, if J equal minus d rho by dt. That's the fundamental law of electric current. Okay. May I continue? Okay. Now we go to the Ohm law. The Ohm law is psi equal sigma E. Sigma here is conductivity. Okay. For the perfect conductor, sigma go to infinity, and for the dielectric perfect dielectric, sigma go to 0. So sigma here represents for the ability of transfer the current, right? So psi proportional to sigma. Okay. In Vietnamese, perfect conductor. In Vietnamese, something we can tell me in Vietnamese, perfect conductor. Okay. Dẫn hoàn hảo, đúng không? Dẫn hoàn hảo. Ở đây là cách điện, đúng không? Sigma, when sigma go to 0, so no electric current. Okay? And perfect conductor, so that super conductivity. Okay. Okay, so we finished the point number 1, we go to the point number 2. Ampere law. Ampere law. Okay, so these beautiful pictures, okay, these very beautiful pictures, is like an egg, right? Very beautiful. Okay. Very beautiful. But it's describing about the Ampere law. Describing about Ampere law. Okay, so let's say, for example, you have the volume V. Okay, you have the volume V inside the magnetic field. Okay, inside the magnetic field. And to express the magnetic field by vector dV. Okay, vector B. Okay, and you have the current density J here, okay, J, and you considering an infinitesimal volume dV, okay. Then you forming the vector R, which is point at the point from the dV to the point which is designed to calculation the magnetic field. And vector R and dV, you forming with an angle alpha, okay, alpha. So the alpha is the angle between the giant and the vector R, okay. So for the Ampere law, you have the dV equal mu by 4 pi r square xi cross r dV, and then you take the all integration over the whole volume V. You obtain the total B at the point R is mu by 4 pi integration V over the own volume G cross R square dV. And R square, which is the distance from the origin to the point which is to decide to conclusion the magnetic field. Okay, so that's the envelope. Okay. Okay, don't confuse. Okay, don't be confused. May I continue? Okay, you take a note. So we just go to the chapter 2, Magnetostatic, with only 1 and 2 points. The first point about electric current and the second point about the envelope. Just only 2 points. Okay. There's not much hurry, right? Okay. Okay. So I remind you about some important quantity. Here for electric, you have the electric field intensity E, you have the electric flux density E, and E and D can be used interchangeable. And for magnetic, you have the magnetic flux density and magnetic field intensity B and H, and again B and H can be used interchangeable. So B and H is the same. We can say that it's the same, just different amount of constant, only a constant. Okay, the magnetic constant. Okay, so two copper symbol here, two copper quantity here is the most important in our electromagnetic courses. Okay, you should remember this. Here H equal P by V, and V here is a magnetic constant. Okay, it's the same as the previous slide, except that H replaced for B. Okay. Okay. We go to the number 3. Topic number 3 is magnetic force. Given you have the charge magnetic Q moving with constant velocity V in the region thus only contains magnetic field with density B, then the force I govern the magnetic is F equal to Q V cross B. Okay. So look at the slide here. Is the charge Q, and this charge in the magnetic region, so you have the vector B, and here is the velocity of charge V. Okay, and then you forming the formula to create the forces F equal QVB. So here is the direction of F, and here is the rule for you to remember. Okay. Okay, so the rule for you to remember is called right hand rule, and here I summarize some point 1, 2, 3, 4, 5 to you remember the right hand rule, just for you to remember. I think it's origin from you learn from high school. then no force it will be either parallel or anti-parallel. Is parallel or anti-parallel. Okay, it's sine 0 and sine 180 equal 0. And the force is maximum when V and B are perpendicular to each other. The sine 90 degree equal 1. Look at this. You have the V, which is the velocity of charge, and B. B here is go from the boat inside, out, goes boat out. Okay? And here, go in the boat. And here is V, and V and B is 90 degree. So that F maximum. The same thing here is V and B is perpendicular. So that F is maximum. Okay, so we go to the exercise. Exercise 3-point arrange in uniform magnetic field and the magnetic field point into the screen. So we have the 3-point A, B, and C. So the question number 1, the positive charge particle is located as polaric and stationary. Then the direction of magnetic force on the particle is number A, number B, number C, number D, E, or F. You have 5 minutes, okay? Okay, we answer that question, that exercise, so then we take the short break for 10 minutes. Okay. So Biot-Savart law is used to compute the magnetic field generated by a steady current that the continuum flow of charge, for example, through a wire, which is constant in time and in which charge is neither building up nor depleting at any point. Okay. So as I told you that Biot-Savart law is very important law in magnetic field and the same role as Coulomb law in electrostatic. We call that the fundamental law of magnetostatic. Okay. And okay, so this very beautiful slide will tell you everything about the Biot-Savart law. Exactly the equation here. Exactly the equation here. It's very beautiful equation. Okay. So you have here E equal V0 by 4 pi integration I cross R hat divided by R squared. Okay, so I will explain gradually. The first is B. B here is the magnetic field which we decided to calculate it. And from the Biot-Savart law, it will become V0 by 4 pi integration I cross R hat divided by R squared. Okay, so for the first element I here is current. Normally it is steady current. So you just pay attention for the end. Okay. A vector whose magnitude is the length of deviation element of y and whose direction is the direction of conventional current. And then here is R squared. R squared, which is the distance from the origin to the point which is designed calculation B. the magnetic field. Okay, so R square is the distance square. Okay, and now for the R hat is unit vector in the direction pointing from the y element toward the point at which the field is being computed. So that's all thing we described about the Biot-Savart law. Okay, it's very important. Okay, so we come up with the exercise. So that exercise, draw this computation B at the point P. Okay, and you have the straight line with the current, constant current I goes to the straight line, and the length of the line is minus A to A. It means that the line lying on y-axis, and draw this find the electric field at the point P far from the origin x in the x-axis. Okay. Okay, it's very good exercise, and you have 10 to 5 to 10 minutes. Okay, so the time for the exercise finished. It's time for the solution. Can any student have the answers? Please go to the board and give the answers. Anyone? Anyone? Okay. Okay, so I will give the answers right now. Firstly, the idea is using the Biot-Savart law. So you try to find each element in Biot-Savart law. Here, Biot-Savart law. You try to find out each element in Biot-Savart law, and then you can calculate the magnetic field at the point P. Okay. So this line also give you something. Okay. The first is vector R. Okay. Here's the element Dn, and the vector R pointing to the point P here. Okay. And here is element Dn. Okay. So it gives you the information, and because this is the straight line, and the current goes to that straight line, so you can calculation the length R here. R is by Pythagoras. Okay, R equal E squared plus Y squared root of E squared plus Y squared. Okay, so each which is the coordinate at the point P. Okay, and Y is the length from the origin to the element N. Okay, so you have the length R already. So the other element is Dn and R. Okay, Dn and R. And because you forming the cross product, okay, so you need the angle between Dn and R. Here is the angle here is C. Okay. C. So you have a lot of information, and because this is the small element, so in your idea you need the integration over the whole length from the minus A to A. Okay. So that's the idea. That's the idea, and then you gradually you specify element. Okay. So here, E, Dn, cross R, and R squared. So now because that the cross product, right? Cross product. So it's will be each element times by cos c, okay? Sin c, sin c is the cos, sin c here exactly is the cos pi minus c, okay? Sin c equal cos pi minus c, and cos pi minus c is xy divided by r, okay? So you have the x here divided by r, which is the root of a squared plus y squared, okay? And now if r is root of e squared minus y squared, so r squared will be e squared plus y squared. So that when we combine it, you have the e squared plus y squared over 3 by 2. Okay? And now you have only one variable for taking integration, that is y. Okay? Y is you take the integration over y. And to find the limitation is from minus a to a. Okay? So it's minus a to a. Okay? And the remaining here is you put outside because I here is constant and here is constant also. Okay? So now Jojo change to one linear integration from minus a to a of this one. Okay? And that's the job of mathematical table. I allow you to use a mathematical table to find the results, or you calculate by your hand if you have a good manipulation scheme. Okay? And then you come up with the result is b equal to mu0 4 pi 2a x root a squared plus a squared. Okay, so that's the result for problem. Okay. So now we continue to expand the result. For example, in the limit case, if a here is much greater than x, okay, it means that we have the long line. And then what happens if a greater than x? We take the limitation from this formula. Okay, a is much greater than x, so that we can discard x. So root of e squared equals x, right? Sorry, a greater than x, so we discard e squared, just only a squared. Root of a squared exactly equal a cancel out, so b equals mu0 I 2 by x. So this is the limited case. One more thing is about the direction of b, right? This magnitude, how about the direction? Okay, I give you the result. Here, the straight line, and I go from this direction, and then here is the direction of b. Okay, the direction of b, prediction given that the I follow the direction of thumb. Here, the direction of thumb is the direction of I. Okay, and then here is the direction of b. Okay, so you forming the b, both magnitude and direction also. Any question for the problem? Okay, so it can be understood. We go to the other problem. Okay. So here is your problem. And the thing is different because now instead of straight line you have the circular. And here is the electrical coming, the current coming and current outside. Okay? And here you have the circular and the electrical going in circular. And now the job is calculation the magnetic field at the point P. And the point P here is lying on the axis far from the origin, the distance x, okay? And the radius of the ring is A. So A is the radius of the loop, and job is here to be of a circular loop. Okay? Okay, so once again you have